start off with some questions here. Oh, just sorry, just a minute. I'll just go to this one. Sorry about that. And we'll just look at putting in some equations. Now, first thing we have to do is we've got the two vectors A, I plus 3j minus 2k, and B equals 3i minus 2j plus k. And just a couple of different ways that we can actually enter this into our calculator. We can go, if we have a look, there's a matrix and vector menu, and we can go through and have a look at some of these to start with. But to start with, what I'm going to do is I'm going to define them. So I'm going to go define, and we wish to define vector A, and I'm going to use the pull-down menu here in this little box, and we can have a look. In this case, because it's a one row and 3 columns, I have to go through quite a bit of tedious stuff just to get to it, and we put it in, and then we have to just type in the values of 1, and we hit tab to get to the next one, 3, tab, and minus 2. Now, I was just mucking around looking at a couple of things on the internet just recently, and I'm going to do the second one, B, in a slightly different way. I'm going to use the assign key this time rather than define. And if I go Control and equals, which is the little blue button up there, I get the assign key. But this time what I'm going to do to put it in, I'm going to go Control and the square brackets. And I'm going to put the second one in, I'm going to go 3, but this time I'm going to press a comma. And then I'll put in my minus 2 and a comma, and we'll put in a 2. And when I press enter, it automatically puts it in and saves that. So I think that's a real time saver. And my aim of today's session is to try to find a way that we can enter things quicker into the CAS calculator. So now we just have to work out 2a, and we notice that the a is bold, so it has been defined, and we'll just put our plus in there and our 3b, and we see the b is defined also. Press enter and it spits it out. Now our columns over here, that's our I, j, and k. So I think matrix, doing all the problems in a matrix is a really great way of doing it, and it's a very simple output that we can just convert to I, j, k. Magnitude of the vector. We have quite an unusual term for this one. So menu, number 7, and we have a look. And if we go to norm, and go to norm, I think that's an unusual way. Now, if we have a look in our var key, we've got A and B defined, so if we really want to just press it in there, we could go A, and we get the norm of it. That's the magnitude. Moving along to the next one. We want to work out a unit vector, so I guess what we could do is we could go and do our division template and put in our A, and over that we'd want to put in our norm B. So again, menu, matrix and vector, norms and norm, and just put an A in there. And that's all good, that's all done, not a problem. If we just have another look at our menu here in this matrix and vector, and if we go down to where it says vector, we also have the function known as unit vector. And we could do that as well, and put the A in, and we get the same answer. So there's two ways of doing that, and the menu system's quite good. Moving along to the next part. We want to find the scalar resolute of the vector A in the direction of vector B. Now, when this is done by hand, all of these things, before I actually pick up the calculator, I go through all these things by hand with the students so they get all the tech-free components done quite well. And then once that's done, we'll then go have a look at the calculator, and we try and find the quickest way of doing it on the calculator. So we can just go through the menus again, matrix, and then down to the vector. And then if we have a look here, we're going to see that we have a dot product. And then we'll say that the dot product of A, and then we'll go back and we'll hit our menu again, and we see it's getting rather tedious. Well, I think it's rather tedious to put in these things by going through the menus, and we're going to put in B, and our scalar resolute is -7 times root 17 divided by 17. Okay, so we'll continue on, and we will see that we want to find the vector resolute. By hand, students find this quite time-consuming. They quite often make a mistake with their numbers, so if it's a multiple choice question, they could do it on their CAS. So again, we'll go through the menu system, matrix and vector, down to the vector, and this time we will pick up our dot product again, and we're going to put in A, comma, and we want to put in unit vector of B, so it's menu, and you can see that it's 1, 2, scroll down, 3, oops, sorry. Much easier on the handheld, I believe, than clicking all these things on the computer software. We go down, we could press C there, and then we wish to do our unit vector, and we go B, and then we've got to do that again. Now this time the students could actually press Shift, a bit hard to do on my touch screen, and then use the arrow keys to scroll across to copy this. So we could put our comma in here, and then we could hold the Shift key down, and then Microsoft commands work, Control C, go across one, Control V for paste, and then we get our answer. Look, too many arguments. Let me see. Oh, okay, I see what happened there. That should be 8 times. I put a comma, and look. Okay. Not quite sure what happened with that, so I'll just go over to my other file that I have here. It looks right, which sometimes happens, and that's what we should get with that. And
yeah.
That is what I typed in, that something happened. Occasionally that will happen with the CAS, and that we see that's the answer. Now,
that was defined earlier in there, wasn't it?
Feeling that with this, we're finding that the menu system is getting a little bit awkward. We'll do one more. We want to find the angle between vector A and B, and we will look up and go to the trig. Trig, cos inverse, and we have to, if you remember, it'll be the dot product of A and B over the norm of A times the norm of B. So we'll put in our division template, and we'll menu, matrix and vector. We want to go C.
And I see you have this in degrees as well.
Product.
For this. Yep.
A, comma B. So the vectors, down again. So menu, matrix and vector. C, I've pressed C this time to bring it up. We want the norm, and I'll just have to go back one because we want the other one for that, matrix and vector. We want the norm, and we want A, and then we're going to put in a time, and we'll go through again. Now again, we could copy this and shift across if it's quicker. For a student to do that, we could do that. So Control C, go across, Control V, and just edit the A and make it a B, and press Enter. Now, you notice there that once we press Enter, normally the CAS does it in exact mode, so as always, we sometimes forget that we want to go Control Enter, and we get our angle of 116 degrees, almost 117 degrees for that answer. Okay, so I hope you've all got a feeling for, at the moment, that the menu system is quite often quite slow, and we get through that. So I'm trying to work out a way that we can actually speed this up with what the students can do and get in this information. So what I've got is, we've got user-defined functions. So these are just shortcuts, and some people call them macros, that the user previously defines on the CAS calculator before they enter an assessment task. So the student will come up and decide, I have to try to work out some things, and if we can do it more quickly with these, then it will save a bit of time. Now, again, we could just get the define, and now when I first did these, if you notice all the rules from previously, they were just a little bit, I guess what we'd say, black box, where we type this stuff into the calculator, and we may not quite understand what's going on, and it just spits out an answer, and we use the answer. So when I actually did these with some students, we said, well, anything you do by hand, you could basically repeat onto the CAS calculator, and therefore it's another learning tool where we're just reinforcing what they've done check-free. So the idea of this one is that the students can write any formula into their CAS and have it stored there for the future. So I'm just going to call this magnitude, and we're going to put in the three variables A, B, and C that we'll get, which are the I, J, K components. And the magnitude, control, square root, A squared plus our B squared plus C squared. And enter. And if we put in what we had before, all I'd do is I'd just write MAG, if that's quicker, and it's bold, so it's predefined, and I'd just put in our numbers we had before, 1, 3, minus 2, and press enter. And that's a quick way. We could do more. We could do the unit vector one, so I'm just going to go over to my other page here, and I'll just show you the unit vector one. Just looking at the time, it's got a lot to get through. So again, we can, instead of using define this time, I used UV for unit vector. Use some letters which are relevant to what you're trying to do, and I suggest that they use more than one letter, because sometimes when we go through and we want to clear the history and we go clear all variables, if it's just one letter, it gets deleted. 2 or more, it generally doesn't delete it. And I've used the assign key again. We've got a 1 by 3 matrix there. And if you notice, I've actually used the magnitude rule that I defined earlier up here. And we can use any user-defined function that we've got and put it in any other rule. So if you think about it, does that save time? I'm just going to hit my var, and we've got our 2 called up, so a student will call it up, and all they have to do is type in the 3 coefficients, 1, 2, 3, press enter, and that may help them and could be a bit quicker. So that's user-defined functions. Now, the user-defined functions are for a calculator page, in this case. Now, what you're going to have, I've got a file which will have all the things that I'm going to do with the answers on that, but I'll have these files I've got here. I've embedded it in our presentation document, but what you'll find is when you download them, I'll have these 3 files separately, and as we go through it, I'll tell you where these files are stored on your computer, so you can just use them. It's a bit easier, so you don't have to copy and paste them out of the current document. Now, the current one that we're doing, this type of user-defined function, which I'm reading off just down here, can only be used in the problem they are defined. So if I went to a new problem, I could not access them on my var key. They would not be defined. So it's in the current problem that you're in the current document. And someone might say that's a little bit of a downfall of the system, but a lot of kids, again, it depends on the kids that you have and how accomplished they are and what they need to do. Now, what I've got in the file that you have, I've gone through and put a comment about what each of these do, unit vector one, and if you have a look at it, it's just like if we did these by hand, as I mentioned earlier, angle between 2 vectors, etc., and it's just reinforcing the rules that they learn. The one I really like the most is the vector resolutes, either parallel or perpendicular to, because it's quite a tedious thing to do by hand. And if we go back probably 4 years in the specials of maths exam, they had a question which was just calculate the vector resolute of A perpendicular to B that was there. And I thought that was a really good question that would be there. So I'll just show you how quick that would be. I'm just going to put in a new page. Okay. If I go to my var, we can see all the ones that are defined. And if I put vector resolute perpendicular, is this one. And all I have to do is put in the coefficients of the vectors. So if it was 4i plus 5j minus 6, and it was the first vector, and the second one was 1, 2, 4. The second one, if we put it in, we find the coefficient I, J, and K here, 94 on 21, 125 on 21, and minus 86. I think that's a real time saver that we could get. So I hope you guys agree with that.
Absolutely.
Yeah, I think that what we're finding is VCAR is now getting a bit of a wind of what we're doing, and they're making the questions harder. So over the last 2 years, yep, they always do that, don't they? Over the last 2 years, they've actually moved away by just saying find the vector resolute, and they've made the questions a little bit more harder. Now, the good things about these style of user-defined functions, I can actually embed them in a solve feature and solve questions using them embedded in. So we'll just have a look at this one. Let A equals 2i plus 3j plus mk and B equals 5i minus 2j plus m squared k, where m is a real constant. If the scalar resolute of A in the direction of B is 31 on the square root of 110, find the value of m. So we can do that without much trouble, and if we can menu 3, 1, solve. And what we want to solve is our scalar resolute parallel. So if we pull that one up, and if we put in our coefficients 2, 3, m, 5, and minus 2, and m squared, and we know that that's going to equal 31 on the square root of 110. So,
hey Chris, just a bit careful there. You'll need a comma between your 5 and negative 2.
Yes,
and always
because you've got those
a little bit fiddly to put in. And again, I'm just looking at to say whether is it easier for us to pull down menus. But this one would take a little bit of work from students doing it. In our 1110, and
and your comment. Chris, if you, as Stephen said, if you just go back inside your brackets there, so you've got your you got your if you arrow up, you can grab the solve command again.
Yeah.
And just hit enter on that when you've got it. Or just enter on that line. Yep, okay, that'll work too. And just that'll work. Now, just after the 5, back a bit.
Yeah,
after the 5.
Yeah, thank you.
Yeah.
So that's all right.
Thanks, Stephen.
Thanks, Stephen, for that.
No worries.
Yeah. So people like that. Now, the thing about this is we get the students to write these up, but they have to practice them. And at the start of the year, it's a good time to do this. And then they'll get familiar with them, and hopefully they'll write a few more of their own. Now, the next thing we're going to look at is the notes page and maths boxes. And maths boxes are wonderful things. And what we can do is this is a notes page, and I'm just aware of the time, so I'll just briefly explain these things here. Write a math box rule for finding the magnitude of vector. So if we put in our vector, now to put in a math box, when we're on the page, we can hit Control-M, and then we type in our equation or whatever it is. If I had a vector A, I could put in my vector A equals, etc. And as soon as I press enter, it calculates it. Now, the magnitude of V is norm, and again, this is what we did before, so we'd have another math box, we'd put in norm, and as soon as I press enter, it activates. Now, a student would do these before they walked into the exam, and have it all set up, something like this, okay? What's happened is I pressed the A from the last page, which overwrote that, so I'll just have to input that again. Just copy this one.
Just in that. Yep.
Control-C and go up here. And all we're doing is we're put my assigned in, Control-C, and press Enter. And you notice as soon as I actually fixed that up, it went and updated everything. So the notes page is great because let's say that was a 4 there. As soon as I type in, you notice the green writing's gone. I must press Enter to activate the math box that's there. As soon as I press Enter, it calculates it, and everything the whole lot's all updated. Now with this, you notice that all the rules are there, and we can type in everything we want all the way down. And we've got cross product perpendicular to both. That's vector perpendicular both, which is the rule. If I click on that, I can see the calculator command that's in there. Now all the math box formulas that I've got on here, I've actually used all the calculator commands. So that's the notes page. Now this notes page that we just had, that's a notes page which will only work on the current document that we're in. Okay. The next thing would be a widget. Now a widget is, as it says, most of you know, is the stopwatch. So widget is a single notes page in a document stored in the My Widgets folder. This is prepared notes containing math boxes that can be ported into any problem of any document. Now this is the exciting bit that I like. The next bit, the problem we've seen before is when we import them, all the math boxes are deactivated. But if we do this, which I worked out in December just gone by, that to activate all the math boxes in the notes page at once, we can select all, which is a Microsoft Command A. We go to Menu, One Actions, and One Evaluate. So if I put in a widget, I would just add number 8, widget. And if you notice, there's a stopwatch we talked about. I've got my vector 1 here, and I just press Add. And when it's imported, it has all the formulas, but none of them have activated. So as I said, if we go Control-A, and then go Menu, One, Actions, and One Evaluate, instantaneously everything is done. Whereas before, if we've watched some other webinars, we'd go down and activate the ones and scroll down and pick the ones, which would take a little bit of time and process inside. Yeah. So I think I think that's a great advantage for these, and it turns widgets into a really worthwhile thing to use in an exam. The only thing with the notes page and the widgets, it's very hard to embed these into another problem like we did when we worked out the scalar resolute. So we user-defined functions can be put in solve functions. It's very hard for the notes page. We have to really know what the question will be on the exam before we can actually do it. The next thing we can do, which is really good, is we've got a My Library that's there, user-defined functions, and this type of UDF can be imported into any problem or document. So we take our user-defined functions, we just do a small modification to the formula, we store that in My Library folder, and as you see, there's some instructions here in the file that is there, and we store it in the My Library folder, and the only thing we have to do when it is different, we have to, once we put the file in the library folder, we refresh the libraries, and then it's all good to go. Now, if we just look at the formulas that are here, the only thing that you notice that is changed from the previous rule, we must use the define that's there, and all we do is we put in libpub. That's all we have to do. So this will only work with define. If I said I put the assigned key here and tried to put libpub in that, it will not work. So you've got to go define, libpub, and then you'll use define function. And the good thing about these is I can call them in from anywhere, and we'll just show you how they get called in. So I've gone doc and refresh libraries, and they're all stored in. So my file's in my library folder, and I do that. If I put in a new page, it's there to the calculator page, and if I go to my catalogue, now 6, normally we go here to work out what the functions are. If we go to 6, that's my libraries, and here, this is the one that I've done. Now, when you do this, you can't put any spaces in the name. We can put spaces, names of other files, but in the library, there must be no spaces, and there's a certain number of characters you need for the name. I think it's about 14 or 16, somewhere around there. And when we click the plus sign, it just comes down. And if we're going to do the dot, let's say the magnitude, one of those, just click on that. It comes up, it tells you where it came from, which is in the library, and then we just put in the numbers 1, 4, 5, reading off that that's IJ components, press enter and it's done. So I think that because we can now take these ones and place them into any problem, any document that is open, and they're stored in the library, it means it doesn't matter what document we've got in. And I think that's the main advantage is the widgets and our user-defined functions stored in the library. Now, I'm just looking at the time, and there was one more thing that I was going to do, but in the file you'll find it was just about there's another multiple choice question where we can use our user-defined functions. And you see I've called this, I've worked out that it's the dot product, and I've called it in from my user-defined function. Remember, I can't do this sort of thing on the notes page. And I've gone through, and this is a question that's occurred on the last 2 VCAR papers as well. It's there. And it's just a thing on sketching parametric equations. It's there. And we can put them in. The one thing I did want to say that some people may not know, if I wanted to change the, I guess I should just say when we put in the functions, we go graph entry edit, and it's up here at parametric when we put them in. If I go up here, I type them in. Just be aware of the scale, the domain, and just be aware of this scale. Sometimes if it's not small enough, you'll find that the 2 endpoints of the graph don't sort of match up where they should. So make that rather small, that's there, and you won't have that issue. And the last thing that I'm going to say is that people may know if I double click on that value, I can change the scales quite easily. It's there. And the other thing you can change is you can actually change these in the values. So if I change that to 2 and press enter, our scale then jumps up. And the hardest thing that I probably looked at was trying to work out where we wanted to do this, work out the Cartesian equation, and that was the hardest thing. And I picked one which has cos and sines in it, which is probably I shouldn't have, because most of them in terms of t. And there was just a little bit of trouble trying to get it to work. And then the interesting thing that was found was when I tried to complete the square and it was 1 equal, I got a negative in all the terms. And if I put equals 1, they were all positive. So that was something interesting. Now, this question, I think, teaches students that it's probably quicker to do that one by hand. And then I've just graphed this on a relations thing. So, sorry, Stephen, I went a couple of minutes over, but I hope that it's all gone well. And sorry about a couple of typing errors that were in there, but I think we get the drift. And please go over, have a look at the files. There's lots of instructions in that, and I think that's all good. And if you get your students starting early, they could do something for kinematics, they can do something for calculus, and they'll get all these build-up of library functions in there, and it just helps them out with the exam.
Absolutely.
Back to you there, Brian.
Yep. Thanks, Chris. And yeah, just a couple of points in that last file. Just note where you're swapping between degrees and where to radians. The file that we're sending through, I can guarantee that it's terrifically constructed with some clever shortcuts in there. I really like the user-defined functions, and in an ironic way, Chris, you did kind of even illustrate that as you're building it, and thank you for sharing the build of how that was done. I know teachers are going to be really particularly interested in the product, which they can share with their students. In the build, it's even though all the CAS operations are in there, it's not hard to make a small error there, which may have been just in brackets, for example.
That's
in
right.
that building for the vector resolutes.
Yeah, I think we're trying to have a chat at the same time as type, and sometimes we miss a few things. But I think that when you do it on the handheld, it's less likely to make those sort of things and our big fingers and all that sort of thing. But the one thing that I'd just like to add to that, all these user-defined functions, the students would keep a copy of that and what they do in their bound reference in any exam, so they can quickly just refer to that page. Oh, yeah, and that's the input. So they don't have to remember it off by heart because they've got their bound reference in there too. And that'll stop a lot of errors as well, yeah. Okay, so I'll hand it back to you.
Yeah, terrific. So the ball is now in Stephen's court. So if you're ready for a share screen there, Stephen. Yeah, that user-defined functions and into the library. And the other trick is we've been using notes pages for a while now. Really, really useful. And I particularly like that that full update Control A menu, was it Actions Evaluate, to just do the whole thing in just one clean sweep, which is really useful for widgets. I found that myself when I was copying page and saving it as a widget. The advantage of a widget, of course, is it can be inserted into any document at any stage. It's just a single page. But, of course, it needs to have everything activated. Very useful files. I know that teachers and students especially will appreciate receiving those. Thank you, Chris. And Stephen.
Yes. Hello, Brian.
Hello, we see your screen.
Yep, all good to go?
All good to go. Reminder to participants, if you want to maximise the screen, the double arrow to the top right of Stephen's calculator screen as you see it.
Excellent. Well, thank you very much, Brian, for handing that over to me. And thank you very much to Chris for that informative presentation. To be completely honest, I've never personally used a UDF before. And looking at that presentation, it certainly sparked the desire to try it out myself. So I'm going to spend tonight trying out some UDFs myself. So thanks, Chris, for that.
You're welcome.
So I'm sure that all the teachers out there are familiar with what rational functions are. So what I might be going through might be previous information, and you might learn a few new things along the way as well. So without further ado, let's make a start. So we're going to look at graphs and the forms of certain rational functions. So before we even get started, I'd like to give you a little rationalization as to why we're doing this. The main thing is that it appears in two areas of study. So I had a look at the VCAS study design for specialist maths in quite a lot of detail over the past few days, and I noticed that in area of study 1, which is functions and graphs, as well as areas of study 2, which is algebra, that rational functions are explicitly mentioned. In area of study 1, it comes up as a graphical representation, so that's of course graphing them. But of course the important things are the intercepts, asymptotic behavior. That's something that students struggle with a lot, as demonstrated with the assessors reports. And then of course we have the nature and location of stationary points and points of inflection. We're also going to be looking at graphs of rational functions of low degree. To be completely honest, low degree is up to interpretation, but going upon history of previous exams, etc., we could safely assume that low degree means 2 and under. So basically constants, linears, and quadratics. And then finally in algebra, we have sums of partial fractions. So the CAS can actually be used to do partial fractions, of course without working, but to get from the initial combined fraction to the separate partial fractions. Okay, so the first thing I'm going to go through is actually just a fully worked example on one particular type of rational function. So I'm just trying to showcase what the calculator can do. So what we've got is we've got a function f of x equals x squared minus 2x minus 8, they're all divided by x squared minus 9. And we want to find the equations of asymptotes and the coordinates of any axis-intercepts, all stationary points, and if there's any points of inflection. Of course, at the end, we're going to sketch the graph. So the first thing we're going to do is I've broken this up into a few notes pages. As Chris has already done, he's shown you how the notes pages work. So this is what I've done here. So the first thing I'm going to be doing is actually analyzing the function by factorizing. So if I just do factor f of x, it factorizes the numerator, it's a quadratic, as well as the denominator. We can also expand it into partial fraction form, and to do that we use the expand command. As you can see, we've got two partial fractions there with the same denominator as our initially factorized function with a +1 at the end. That will come in handy later on. And the next thing is we have vertical asymptotes. So if you look at the denominator of either the factorized version or the partial fraction version, both of them have denominators of x minus 3 and x plus 3. So clearly what's going to happen is we're going to have vertical asymptotes at these particular x values. So if we use the solve command and the get denom, I'll explain that a bit later, But if we use those two commands together, we end up with x equals -3 or x equals 3. Moving on, we can now consider the long-term behavior of y equals fx. So this is now looking more at the horizontal asymptote. Now, I see that I haven't really activated that box, so I probably should do that. And there we go. So we can see that the limit as x tends to infinity of our function is equal to 1. So that means as x tends towards the positive infinity side, it will equal 1. If you want to check out the behavior of the function as x approaches negative infinity, it's also equal to 1. So 1 is basically our horizontal asymptote. What we can also do is do another quick analysis. Now, this is something that a lot of people don't know about, but if you go back to the partial fraction representation of f of x and just take the two fractions without the +1 at the end, so just these two fractions here, and you get the numerator of them, so you combine them together with the get num, and you equate that to 0, you get an x value of 1/2. Now that x value tells you the point at which your function will cross the horizontal asymptote. And that also leads to good discussions regarding what's the meaning of an asymptote, and also clears up misconceptions about functions not having to cross asymptotes. Because a lot of students, unfortunately, think that an asymptote cannot be crossed. Well, it can be crossed as long as the long-term behavior of the function is towards the asymptote. So that is a really good sort of catalyst for discussion in your classroom. So I'll be sure to get that discussion going when I eventually get to this topic. Moving on to the X-Intercepts. So to get the X-Intercepts, well, it's quite simple. I'm going to grab the numerator of the function, equate that to 0, and we end up with two X-Intercepts at -2 and 4. Moving on to the Y-intercept, all we have to do really is plug in 0 into the function. We end up with 8 on 9. So we've now got this, I guess you could call it a smorgasbord of information regarding asymptotes, intercepts, various other things. So now we can finally move on to some coordinates of stationary points. So what I've done is I've defined df of x as the first derivative of our function f of x. And then I've gone and solved that particular new function equal to 0 for x and ended up with a false result. So what that means is basically our function f of x does not have any stationary points. Pretty straightforward. We can move on to some inflection. So now I've gone and defined f double dash of x as dd of fx. So double derivative, I guess you could call that. The double derivative as the d squared over dx squared fx. And I've solved that equal to 0. Now, from my previous working, the actual exact value of that x value is quite clunky and unwieldy. So I've used the approx command to sort of simplify it into a more handleable decimal representation. Of course, I've then taken that decimal representation, thrown it back into the function, and ended up with the y value. So we end up with the point of inflection at 0.168, 0.926. That pretty much is the end of all the algebra we have to do. So it's quickly now time to get to the graph. Now, I've already pre-prepared this. So on a graph, as you can see, we've got our horizontal asymptotes at x equals -3 and x equals 3. We've got our sort of hyperbolic arms on the left and the right-hand side. Our x-intercepts at 4, 0 and -2, 0. And just in that middle part there, it's a bit crowded there, unfortunately, but I've got the y-intercept at 0,89, which is right there. And I've got the point of inflection at 0.168.926. So if you wanted to look into these sort of points a bit more, you can actually use your zoom in command and just keep zooming in, and then eventually you'll get to the 2 points being distinct. You can press Control Z to sort of get back out, and then we end up back at the same graph. So just take into account we've got our horizontal asymptote at y equals 1, and vertical asymptotes at x equals 3 and x equals -3. So that's just showing you the power of what the CAS can do. Let's now work through one question. So I've got the function fx equal x squared plus 4 over x squared minus 5x plus 4. We're going to repeat the same thing that we did before, aka asymptotes, intercepts, etc., etc. So I've got a blank calculator page, and we're going to start doing the same thing from there. So the first thing I'm going to do is actually define this function. I notice it hasn't been defined yet. So to define a function, I can press f of x, and a really quick way to define, as Chris has shown, is control and template. That puts a semicolon as well as an equal sign, and that is the definition. So looking back at the function, it was x squared plus 4. So before I do that, I'm going to press control and divide. So we get x squared plus 4 over x squared minus 5x plus 4. Just checking that. Yes, that's the same thing. So we now defined the function. So now I'm going to go and factorize it. So menu, algebra, factor. And rather than typing out the entire function again, we've just defined it. So you can press var, and f is already there. So just type in x, close the bracket, comma x, enter. So as you can imagine, just the denominator is going to factorize, and there it is. It's gone and factorized itself. So what I'm going to do now is find the equations of any vertical asymptotes. So what I can do is go to menu, algebra, come down to fraction tools, and get denominator. So as you saw before, we had this complicated fraction here, and I just want to solve the denominator equal to 0. So rather than typing out the denominator or copying and pasting, I can just type get denom, press up once, press enter, and it's copied the thing. It's copied the entire fraction, and we can put we can put get denom, and now it's extracted the denominator. So then we can go ahead and solve it. So menu, algebra, solve, and we can take the previous command, equals 0, comma x. So we can see that there are two vertical asymptotes, one at x equals 1 and the other at x equals 4. So we've done the vertical asymptotes. Now let's look at any horizontal asymptotes. To get horizontal asymptotes, we can either use the expand command to get it into partial fraction form. So we can press var again, fx, and that's expanded it. So again, as we can see, as before, we have a +1 at the end. So we can safely say that that is the value of the horizontal asymptote. Just to quickly verify that, we can go to menu, calculus, limit. And the limit, we want x. We press the tab button, press pi, press infinity, then go back to the big bracket, take your function, or you can type fx there if you prefer, and we get 1. So far, just a quick recap. We have vertical asymptotes at 1 and 4, x equals 1 and x equals 4, and the horizontal asymptote at x equals 1. So now let's quickly look at the stationary points. So what I'm going to do is find the derivative. So a quick way to get the derivative, some of you might know this, is shift minus. So rather than going menu, calculus, derivative, you can actually get there much quicker by using shift and minus. So we've done that. We get d dx, and we want, again, f of x. You end up with the derivative looking like that, certainly much easier on the calculator compared to by hand. And then menu 3, 1 for solve, up, enter, equals 0, comma x. And there you end up with x equals -2 or x equals +2. So there we go. There is our two stationary points. Now let's go and find any points of inflection. To get points of inflection, unfortunately, you can't do shift minus. The best way to do that, I reckon, is to press the template command, the one we used for the assign command, and then the very last button on the second row, you can see a little d and a 2. You press that, and you get the second derivative. So again, you can go to x and keep tabbing until you get to the box. Go var again, f of x, and there you get your second derivative. And of course, to find the inflection point, we can go menu, 3, 1, up, enter, equals 0, comma x. So you get that as your x value of the point of inflection. We can then press Control Enter to get an idea of the approximate value. So about approximately negative 4.11. So that pretty much concludes the algebra for this particular graph. So I'm going to go now to a blank graph page. Notice how I've sort of predefined my scale. So I'm letting it go from negative 12 to 14 in increments of 2. And on the y-axis, I'm going from negative 10 to positive 10 in increments of 2 as well. So to get the entry line, you can see there's no entry line here. You can either press the Tab button, which will get the entry line. Alternatively, you can press Control G. So Control G or Tab gets you to the entry line. Again, instead of typing out the function, we can press var, F is there, press X, and there's our function done. So now what you obviously want to do is get the asymptotes, etc. in. So if you remember back from our calculator page, if you scroll back up, we had vertical asymptotes at x equals 1 and x equals 4. So going back here, what we need to do is get a particular graph entry. And you get that by going Menu, Graph Entry, Equation Templates, Menu, Graph Entry. Correct, relation does the job as well. Yeah, you might try the relation there. So we get x equals 1. There we go. Unfortunately, it's blue as well. What we can do is you can right-click, that's on the computer, or if you're on the handheld, you can press Control and Menu. So on the handheld, Control menu is right-click, and on the computer, of course, right-click is the normal right-click. You can then change the color. I personally prefer my asymptotes to be red, but at the same time, it's a vertical line. We need it to be dashed according to the rules for asymptotes. So again, I'm going to right-click, go to Attributes, go to the next one, and change it to dashed. And there we go. We have a first asymptote at x equals 1. Likewise, we can press Tab again to get the second relation, and press type in x equals 4. This time, luckily, it has come up red, so we don't need to change the color this time. And I'm going to right-click that.
Yes.
That's correct, yeah. And change the attributes to dashed. And there, we've got our 2 vertical asymptotes. And not only that, you get an extra bonus. The calculator has already put the labels for you. How good is that? So now let's move on to the horizontal asymptote. Again, I'm going to press Tab. And in our relation, we can type in y equals 1. And there is our horizontal asymptote. Unfortunately, it's black this time. So let's go and change the color to red. Right-click that, attributes, dashed, and there we are. Okay, so that's taken care of. And you can see y equals 1 appear there as well. So we've almost done everything. The only thing we haven't really done yet is the turning point. So of course, I'm sure many of you know this. If you go Menu, Analyze Maximum, because we have a maximum here, we're going to click on the graph that we're trying to analyze. Go anywhere to the left of the stationary point, click Enter. Anywhere to the right of the stationary point, click Enter, and we end up with 2, negative 4. So as you saw,
a good illustration of where the domain is very important, isn't it?
That's exactly right.
It's only a local maximum. Yep.
That's right. So that's a local maximum. So that was x equals 2 taken care of. If you go back to your calculator screen, you actually see another x value, which is negative 2. So let's go back to our graph, and you can actually see that this graph comes down and sort of bounces back up. So that kind of tells us that there might be another stationary point there. So let's analyze it. Menu, Analyze, but this time it's going to be a local minimum. Again, choose the F1 graph. Left, right, and exactly what we thought. There is a local minimum. Even though you can't see it very well, there is a local minimum at negative 2, 0.444. Now, in saying this, we'd like to have exact values on here, just to check whether that is indeed the value or not. You can actually try something pretty nifty. If you hover your hand over that point, over that number, and then press the plus button, you can see that there's more decimal places. So this is leading us to think that maybe that's 0.4 recurring, and it keeps going on. Now, you might know that 0.4 recurring is the same as 4/9. So I'm going to double-click that, type in 4 divided by 9, hit enter, and it says invalid input, but it turns out it still did it. So that means that it's actually -2,49. So if you wanted to use this as an example for your class and screenshot this and hand it out to your students, at least you've got a 4/9 sitting there rather than 0.4 recurring, just because we know the value of exact values, especially with examinations and not approximating things without being asked to do so. So that pretty much takes care of all of those. If I'm not mistaken, there's only one thing left to go, which is the inflection point, which is happening at about -4. So I'm going to go back to the graph, press menu, analyze inflection. It's going to be the blue graph, go all the way to the left, take it slowly to the right, and we end up with our inflection point right there. If you'd like to put an arrow for that, you can of course do it with menu, geometry, points and lines, and you can actually create a vector. So you create a vector from any point you want towards the inflection point, which is right there. So you can actually create vectors to show things visually like that. It's pretty, you can do some pretty awesome stuff with the CAS as long as you know where commands are and how to use it. So that pretty much concludes the graph there. We've got the entire graph, we've got all the asymptotes, we've got, there's no X-Intercepts. One thing I forgot was the Y-intercept, so I'll quickly take you through that. Menu, trace, and graph trace. So menu, trace, graph trace, then you type in the number 0, press enter, it snaps you to the point where x equals 0, which is 0, 1. You press enter again, and it places the coordinate there. So as you can see, we have a y-intercept at 0, 1. Okay, so I'm looking at the time, and if you don't mind, Brian, I'll just go quickly through a couple more things.
Yep, certainly.
Sure thing. All right, so the next...
Yep. I was going to say, we also do those intersects with an intersection, but yep, that works as well.
That's correct, exactly right. You can intersect the asymptote and the graph itself. Very good.
Yep.
Okay, so the next thing is quickly, it's a point of discontinuity. Now, with a function such as x plus 5 over x squared plus 6x plus 5, if you factorize the entire thing, you'll notice that the numerator and denominator in fact share the exact same expression, which is x plus 5. So what this means is that you could, I guess, in elementary math, cancel it out. But if you think about it a bit more, we can't cancel it out because then we would be allowing a division by 0 when x equals -5, and that is not allowed. So what that actually is representing is a point of discontinuity. And if you look at the graph, which is here, it looks like a simple rectangular hyperbola, which is moved to the left by 1. However, at x equals -5, we actually have what's colloquially known as a hole. So what that means is the function is defined everywhere, apart from -1, of course, as well as at -5. So just to sort of make that a bit more clear, you can actually expand this on the calculator, and it will say 1 over x plus 1, but it will come up with a little domain error. Another way to really show this is that if you have, if you try a trace, oh, what happened there? If you try a trace at any value close to -5, and you start moving your value, and you try a -5, it says it's undefined. And you start moving it around, and again, it shows undefined. So it just goes to show that you have a hole over there. Unfortunately, the calculator will not display it. I personally put that point over there, but if I remove that point, the graph will look like a normal hyperbola. So it's just something to be aware of when you're doing functions like this.
Also
so I'll quickly
shows up
end
beautifully in a table, I think. Yep. Sorry, Stephen. I was just going to say,
exactly right.
A table of values is often beautiful for illustrating that.
That's exactly right. So
I'm just wondering
if you'd
also,
like to,
the orange circle that you put on there, or the orange point, is it worth just mentioning to the viewers how you get that in? as a point, and you've shown us already how to put a vector in for the arrow.
Yep. Yep.
The orange point, how was that created for your illustrative purposes?
Awesome. So the way I put the point there is I just, again, use the geometry menu. So menu, geometry, points and lines, and I just put point. And you can place a point anywhere you want. So I decided to place it at that particular point. So of course, when there was free space there, I put it there, and then you can change the X and Y values as you please to get that point there, and then you can start changing the attributes. You can make it.
Yep.
Yes, you can make it an open circle. Unfilled circle, and you can change the color, of course, like that.
Very
so,
so
you can just use the geometry command to place points where you like, and then of course do things like that. It's really cool stuff.
Thank you.
Awesome. All right. So just what I'll quickly finish off with is an addition of ordinates view. So in specialist maths, we effectively fall into four sections with addition of ordinates. You can either have linear functions and hyperbolas, or linear functions and truncus, quadratic and hyperbola, or quadratic and truncus. So linear and hyperbola effectively boils down to ax plus b plus c over x. So I'll quickly go through this in the interest of time. But what I've got here is I've created a notes page on the left-hand side and split screen it with a graph on the right-hand side. So the first slider is A values, second is B, and the next one is C. So those values of A, B, and C are basically piggybacking of this function over here, ax plus b plus c over x. So what I really like these sliders for is you can start modifying them, and if you have this on a projector in your classroom, you can really show the students what the effect of all these coefficients are. So for example, the value of A, of course, affects the gradient because that's ax plus b. The value of b will affect the y-intercept of your linear function, and the value of c affects the dilation factor that's occurring in your hyperbola, at least before the addition of ordinates took place. What I really like about this as well is that this line here is an asymptote, but in fact, it's nothing special. I've just made a second function, called it a times x plus b, and then changed the attributes to be dashed. So what that's done, it's twofold things. We're drawing a line, but it's also showing the effect of how the asymptote changes in conjunction with our final graph after addition of ordinates has taken place. It's really nifty feature. You can change A values to positive, negative, change your B values, and change your C values, of course. So in terms of a visual demonstration, it's absolutely powerful stuff. Again, we have linear and truncus. Same thing happens. You can change your value of A, which will change the gradient of your asymptote. We have B, changes the y-intercept of the asymptote, and C, which changes your dilation factor of the truncus. So that's there. And let's finish off with two more, which is a quadratic and a hyperbola. So if you add a quadratic and a hyperbola together, you get some quite nice looking graphs. Now, if you do this by hand, it's quite dodgy stuff. But if you do it on the calculator, you get you see the actual beauty in the graphs that you're presenting. And this is probably one of my favorites. If you're adding a quadratic and a truncus, you get a quadratic, you get a parabolic asymptote, and you get your truncus being pushed up. So the way I like to explain this to my students, and you might like to do this as well, is imagine you have a truncus such as this blue one here, and then if you suddenly add a parabola to it, it effectively takes this asymptote on the x-axis and pushes the graph up according to the stencil of the parabola. So you can see with a equals 0, there's no parabola. As soon as you make a equals 1, suddenly you've got a parabola going up like that. Unfortunately, my skills don't extend to showing that as an animation, but I'm sure Brian or Chris, you would have some sort of experience with that. But basically, that is how you can show the various transformations as well as addition of ordinates occurring with linears, quadratics, truncuses, and hyperbolas. I hope you all found that helpful.
I think demonstrations are brilliant because you can visually see them really quickly. I think that's a great way to show all the concepts of changing the values.
That's exactly right, yeah, because the majority of students will be are very visual learners, and the technology of Nspire CAS is really brilliant for showing those. So that's great.
Yeah, I really liked, as you say, the dynamic visuals there. The animation is just a small step away. It's just automatically animating those sliders.
Oh, that's right. Yes.
Yep. But I quite like the idea of being able to explore values and just type them in. For example, what happened when A equals 0, and then the dramatic, no parabola, then the dramatic change, of course, when A equaled 1.
That's right.
Yep, absolutely terrific for helping the understanding there, illustrating the big ideas, and making it a topic that's very accessible for the students. Thank you very much, Stephen. As I said, participants, did I not promise right at the start, you've got some great files there on the way, and I wish I had them a couple of years ago. So thank you to Stephen for his clever ideas there. We look forward to hearing more from Stephen in our webinar program this year, as we also do from Chris. Thank you, Chris, who took us through the use of defined functions, the library, the notes page, and the widgets for the vectors. A wealth of information there. I am aware that we've now gone beyond our defined time, but if you do have any remaining questions, now is your chance to type them in. Just type it into the Q&A, direct it to all panelists. I won't see that at the moment because I'm presenting, but our two main presenters, of course, will see it and may be able to give you a quick response there. Of course, you can also use that to express your gratitude and accolades for the wonderful presentations that they have just done. So thank you all to there. That is our time up. I do have a couple of other things that I've been asked to notify you about. You will be getting feedback or asked to fill in the feedback form when you exit the webinar. If you have to exit now, if you've got other things in your evening, thank you for joining us and all the best. Just a reminder, though, that you will be getting, within the next couple of days, a follow-up email, your professional development certificate for attending this training. And that email will contain those wonderful files that you just saw illustrated. So farewell if you leave us now, but if you do have 5 minutes to spare, could I just mention some other material that is coming your way that you may wish to tune into? First of all, on that professional development theme, so you get your presentation, you get your certificate for attending this webinar and listening to the words of wisdom from Chris and Stephen. The next step, while you are exploring your professional development, would you be interested in sharing your TI tech-driven lesson idea? I'm sure Chris and Stephen wouldn't mind me saying they are both fresh cabs off the rank from last year. So both did their first webinars with our program last year, and look how accomplished they both are. So if you would like to share, initially just a 5 to 10 minute guest segment incorporated into one of our other webinars, type your expression of interest now into the chat window. It's not a commitment. It's just saying, hey, you'd be happy to have someone contact you to discuss it. John Bayment is our other host, so either John or myself would contact you via email to ask you about your idea. If you do wish to go ahead, we'll schedule you in a guest spot, but not before we give you some training in advance on the WebEx system. So more on that. If you are watching via a recording, obviously you can't talk to us in the chat. just send us an email. You see my email address at the bottom of your screen. And how is it that you could be watching this as a recording? Two ways. One, you may have accessed it via the on-demand section from the Texas Instruments Australia website under the professional development section. You don't want to go typing all that in. It's a big, long bit. Just go Texas Instruments Australia and click on the Teachers section, and you will be able to navigate to the webinars. Alternatively, you could visit our YouTube channel, and you can see that's the address there, fairly straightforward. I will give you a copy of this presentation so that you have these links. But also coming up, if you prefer the live webinars, this is the program for Term 1. So you see, coming up, we have a 2-week break, and then on the 13th of March, we have Maths Methods, Inverse and Composite Functions. That's on the Tuesday. On the Wednesday, we have Further and General Mathematics, particularly focusing on time series data. And then in the final week of, not the final week of term, but the one after that, middle school mathematics, TI-84 technology, and then middle school mathematics with TI-Nspire. So book into those, again, via the Teacher Professional Development section of the website. Or you might be getting this through the newsletter. If you want to attend face-to-face professional development, can I especially draw your attention to this? In 3 dates coming up, the 9th of March, Specialist Mathematics, that's our topic of today. But to take that even further, 9th of March, and on the 16th of March, Maths Methods, and on the 23rd of March, we've got General and Further Maths. Now, these face-to-face professional development sessions will be at Scoresby in eastern Melbourne, at the Texas Instruments office. And look at this part here. Are you a regional Victorian teacher, a country kid like me? Texas Instruments is even offering a limited amount of complimentary accommodation. So that's a great one to take a look at. Could I just point out the 23rd of March I will be presenting at. So that's that general mathematics and further mathematics session on Friday the 23rd of March. Now that means if you are a country kid visiting Melbourne, you will be there on Thursday the 22nd of March, which of course is the start of the AFL 2018 season and would give you an opportunity to see the 2017 flag unfurled at the MCG at the Richmond Carlton match. If you're going to go to that, give me a yell. We could travel together to Scoresby after the game. What do you reckon, Chris?
Yeah, I guess we could. It wouldn't be too bad.
That sounds like a great day out.
Great one. So that almost brings us to the conclusion there. If you're wondering where to find information on those things, as I said, teacher resource section on the website. You see on your left there the webinar program, on the right the face-to-face workshops program. That's the link, but it's easy to find it just by Googling Texas Instruments Australia and follow the teachers section from there. Alternatively, you may be getting news of this via the newsletter that's sent out. You can see that I've hot linked it here. When you get this PowerPoint, you could do as I have and just click on that. It would take you to a web version of this newsletter. It may have been this that brought you to this very webinar that we look at now. This was mailed out, I think, about the 7th of February, mentioning our Term 1 webinar program. Well, first of all, the volume purchase program. schools, if you're at the stage where you've just bought, or your students have just bought all their technology for the year, keep a copy of that invoice, because you can use that to get extra technology for free. Such an example could be the TI-Innovator system. Get a few units of those for your classroom, or you could do as I did with my school and used it to get some of the Wi-Fi caps to work with the Navigator system. Check that out. And here we have the Professional Development Face-to-Face program. Learn, Energize, Connect is the name of the program. There's the 3 dates I've mentioned: 9th of March, Specialist Maths; 16th of March, Maths Methods; 23rd of March, General and Further Maths, all at 44 Lakeview Drive, Scoresby. And remember, that's limited amount of accommodation for country kids such as myself. And you can click on here and follow it through. If you are not receiving that newsletter but would like to do so, then you can subscribe to that. Guess what? Once again, that is through the website in the teacher support section. If you have any other further questions, either of these numbers will work, depending which of those countries you are in, to speak to the office, Texas Instruments office directly. So, once again, thank you for tuning in. Thank you especially to our 2 excellent presenters this evening, Stephen and Chris.
Thank you, Brian. And thank you, Chris.
Thank you, Brian and Stephen. That was great.
And we look forward to hearing from you more during the year. And thank you, viewers, and good night to all.
Good night, everyone.
Night, everyone.